intro to matrices. Matrix is, basically an array of numbers, which can be represented in a lot of different ways. So I'm going to represent it in a very general way first. So we'll say Aij. Actually, let me go with A11. I'll show you what I mean in a second. A12, A13, A1J, A21, A22, A23, A2J, all the way down to AI1, AI2, Aij. So you see a matrix represented as, a bunch of, like, let's say floating numbers in this big bracket thing. And obviously a matrix can be represented in many different ways. And, you see I wrote I and I wrote J. I represents the row number and J represents the column number. And Aij represents a specific element in the matrix, which is, which is a number in the matrix, or a variable, or an expression, or whatever. This is the element in the matrix in row I and column J. So that's why this one is A11. So this is an element in row 1, column 1. This is an element in row 1, column 2, A12. A13 is a element in row 1, column 3. A21 is an element in row 2, column 1. So always row and then column, row and then column, row 2, column 2, row 2, column 3, row 2, column J, whatever it might be. Row I, column 1, row I, column 2, right? So this is the general representation of a matrix. So if I have random matrix, here's a matrix, and I ask for the following elements. Yes and no, Leland. Kind of. Not necessarily horizontal. I guess you could look at it like that. So this is an example of a matrix. And let's just assume that I ask you for the element A11. So we always know that it goes row first, column, row first, then column. So this is A11. This is the element in row 1, column 1. So for this particular matrix, the first row is here. The first column is here. So the element in row 1, column 1 is 2. So this element is equal to 2. Let's say I ask you for A22. This is the element from this particular matrix. This is just one particular matrix in row 2 and column 2. Row 2, column 2, that element is 8. Let's say that I ask for A31. This is the element in row 3, column 1. But this matrix does not have a row 3. Therefore, well, I won't put X. We'll put does not exist, okay? Does not exist. So, that might try to trick you. But if I go A23, this is the element in row 2, column 3, row 2, column 3, 9. Okay, so this is just a way of like asking for specific elements or representing specific elements in a matrix. Okay? Now, what we call the dimension of a matrix. And the dimensions of a matrix is basically I cross J. So again, how many rows by how many columns? So if I look at this particular matrix and I want to find the dimension of this matrix, I would say that this matrix is, so how many rows does it have? 2 rows and 3 columns. It's a 2 by 3 matrix. So the dimension of this matrix is 2 by 3. Obviously, I can have a crap ton of different types of matrices, right? Let's say that I have another matrix, another random matrix. 2, 3, 4, 5, -1, -2, whatever. I don't know, making stuff up. 0, 0, 7, 8. Here's a matrix. What is the dimension of this matrix? Well, how many rows does it have? It has 3 rows. And then how many columns does it have? It has 4 columns, a 3 by 4 matrix. And the dimension of a matrix is very important because it's going to tell you if you could do certain things or cannot do certain things. This is a 3 by 4 matrix. Let's say that I want you to find the element A32. What does that equal to? Well, that's the element from this particular matrix in row 3, column 2, row 3, column 2, which in this case is 0. Good. What about A34? This is the element from this matrix in row 3, column 4, 8. A13. This is the element from this particular matrix in row 1, column 3, row 1, column 3, which is equal to 4, okay? Not bad, right? So far, so good. I'm just talking about some terminology involved with matrices. Square matrices have equal, so they have the same number of rows and columns. Same number of rows and columns. So 2, 4, 7, 8 is a square matrix. This is a 2 by 2 matrix. Has 2 rows and 2 columns. This one is a 3 by 4. This is not a square matrix because it does not have an equivalent number of rows and columns. This is a 2 by 3. This is not a square matrix because it does not have the same number of rows and columns. 4, 8, 9, -1, 2, 3, 5, 7, -3, 0, whatever, 1, 1. -4, -3, 0, 2. This is a 4 rows, 4 columns. This is a 4 by 4 matrix. This is also a square matrix because it has the same number of rows and columns. So square matrices have equal number of rows and columns. And some stuff we could do with only square matrices. You'll see different things. Equivalent matrices. This is pretty basic common knowledge, but like logical knowledge. Equivalent matrices, equal matrices have same number of rows and columns and equal elements, equal corresponding elements. That would make sense because otherwise they would not be equivalent matrices. Equal corresponding elements. So for example, 2, 7, 8, 1, 9, 4 is supposedly equal to x, y, z, 1, 9, 4, for whatever. So here's a matrix that has 2 rows and 3 columns. Here's a matrix that has 2 rows and 3 columns, and I claim that these 2 matrices are equivalent. Obviously, they have to have the same elements in the same location. So you can see the bottom row, they have that. Sometimes you're asked to find each variable, find the variables. I made it a very easy situation, but obviously, if x is here and 2 is here and they are equal matrices, then x must be 2. If y is in row 1, column 2, and so is 7 in this matrix, and they're supposed to be equal, then y must be 7, right? Z is in, row 1, column 3, so is 8. They're supposed to be equal matrices, so that means that Z should be 8. So sometimes you get situations where they say, solve for x, y, or z, and then you get these type of equations that you have to set up. And sometimes you get a system of equations. It just depends on the situation. One more thing I want to talk about, you're going to hear me talk about throughout Chapter 8, identity matrices. Which is represented by, how do they represent it in your book? I don't know. Where is it? Whatever. You're going to see capital I. Let's say I2. So I2 is the identity matrix, and an identity matrix has ones down the diagonal of the matrix, and zeros everywhere else. And they're only square matrices. So an identity matrix is a square matrix that has ones down the diagonal and zeros everywhere else. So if I have I2, this is a 2 by 2 matrix, ones down the diagonals and zeros everywhere else. It kind of acts like, so the identity matrix kind of acts like the identity in multiplication, which is 1. If you multiply anything times 1, you get itself. So if I multiply any matrix by the identity matrix, I get itself, the original matrix. And the identity matrix is used in different ways. You're going to see it again. But let's say I3, so this is a 3 by 3 matrix. Ones down the diagonal and zeros everywhere else. Okay, it has to be a square matrix. So I4 is the identity matrix with ones down the, it's a 4 by 4 matrix. Ones down the diagonal and zeros everywhere else. Okay, so these are called identity matrices. Again, they act like the number 1 in multiplication. So obviously you can have any kind of like identity matrix as long as it's a square matrix and down the diagonal you have ones and everywhere else you have zeros. So let's